what do we have going on here? So this part goes to 0, so that's fine. Now, what about this part? As long as, for the rest of this, as long as there's no danger of it like going off to infinity or something, then we're fine. If this is at least bounded, then it can't interfere with this part going to 0. So what can we say about this? What's the largest it can possibly get? Yeah, 1. If y is equal to 1, then this whole thing becomes 1. And certainly this thing can be as small as 0. It's going to be non-negative. So this whole thing lies in this interval. So it's not going to be able to stop this part from going to 0. The whole thing is 0. So f is differentiable at this point. So we confirmed that the linearization is a good enough approximation to a function at that point so that this error divided by the difference in x values, that magnitude of the difference, goes to 0. The main point is that this part is at least bounded. So as xy goes to 1, 1, then this part's going to 0, and it's going to be multiplied by some number between 0 and 1 all the way through as x and y approach. So it's impossible to have a situation where this is going to fail to go to 0. The only way that could happen is if this could potentially become infinite, to offset this going to 0.
Right.
Because something that's bounded times something that's going to 0 is still going to go to 0. Single variable case, the chain rule, you're given two functions f and g. The composition of f and g is often written this way, f circle g. So this is a new function, and it's defined to be f of g of x. So we're chaining functions together. So now, the way we compute the derivative of a composition, that's where the chain rule comes into play. Just refresh your memories. That the derivative of the composition at x, take f prime, so derivatives of both functions are involved. F prime, and this is where everyone messes up. Not everyone, but a lot of people. You evaluate it not at x, but at g of x. It's very important that you remember to put that in there, times g prime of x. So we have a multiplication of derivatives going on here. The derivative of the outer function is evaluated at the inner function. So those are the two main things to remember about the chain rule that apply in the single variable and the multivariable case. So what I'm going to do is I'll state the chain rule in the multivariable case, so you can see the similarity between the two. So a multivariable chain rule, suppose you have a function f, takes in n variables, outputs m of them. Then you have an inner function g, takes in p variables, and it outputs n. So these have to match. So because the output of g is going to serve as the input to n. So these two have to be the same. So the composition, we have a point x in Rp, then the composition is defined in a similar way. So it's f, right, these could be vector valued functions, f of g of x. So x is a vector of p elements, g of x is a vector with n elements that's plugged into f, and the output of f is a vector with m elements. So it's still the same idea, garbage into one, garbage out, becomes garbage into the next one, so we have twice baked garbage. F has a Jacobian matrix of first partial derivatives. Actually, instead of x, I'll use y. So y belongs to Rn. I think that's what f takes in. So all the first partial derivatives go in here. Because f has m component functions, and we're differentiating it with respect to all of the variables. So this is a matrix, n columns, m rows. Same is true for g, but so we have the matrix jg x, but it's set up in the same way, but it has p columns, n rows, because this is the number of variables it takes in, this is how many it outputs. And I'll make this all concrete after I state the chain rule, and then we get into examples. But I want to see how the multivariable chain rule really is the same as the single variable case. So what the chain rule says is that the Jacobian matrix of the composition f composed of g at x, at any point x, we'll say x naught, so any particular point you choose, is equal to the product of Jacobian of f evaluated at g of x naught multiplied with Jacobian of g evaluated at x naught. So compare that the single variable case and we have a multivariable case. And we take the derivative of f, and this matrix is referred to in Marsden as the derivative. So we take all this matrix partial derivatives, multiply it with this matrix of partial derivatives, and the ones of f are evaluated at g of x naught, the partial derivatives of g are evaluated at x naught. Exactly the same thing that's going on down here, where matrix multiplication reduces to ordinary multiplication. So I'm going to be saying this all semester long, it's all the same thing. Let's have f, the function of three variables that just outputs a scalar, g, the function of one variable, but it outputs a vector. So that means that f composed with g is just a scalar valued function of one variable. So let's give some formulas. So f of x, y, z is e to the z cosine 2x sine 3y, and g of t, the vector, so it's 2t, t squared, t cubed. So the composition, function of t, so it's going to be e to the t cubed cosine 4t sine 3t squared. So we're clearing what the composition looks like. Two ways we can differentiate this. So we can either work with this and just differentiate it with respect to t directly, or differentiate f and g and take those individual partial derivatives and combine them using the chain rule, and that's what we're going to do. So first, for f, function of three variables, we compute the gradient. So that's going to be a row vector of partial derivatives with respect to x, y, and z. So we go ahead and compute those, and what we get is minus 2 e to the z sine 2x sine 3y. So that's the first one, that's fx. Then we have 3 e to the z cosine 2x cosine 3y, that's fy. And then we have e to the z cosine 2x sine 3y, that's fz. All right, so that's f. We need a derivative of g now. G prime of t. So when functions are vector valued, I'll write them two different ways. Sometimes it's more convenient to write it this way, with the same notation that was used last semester, or it should be written as a column vector. And for purposes of matrix multiplication, it really should be written as a column vector, because that's the only operation that would make sense. So we would have 2t, and 3t squared. So we just take the derivatives of b, so this is a single variable differentiation with respect to t. So now, take f composed of g, function of a single variable, its derivative with respect to t is going to be the gradient of f at g of t. So we're going to take the component functions of g of t and fill them in for x, y, and z down here times this vector. You can think of this, if you like, as a dot product. That's exactly what it is, in fact, because we have a row vector times a column vector. So to write out what's going on here, the gradient evaluated at g of t is going to be, so we have minus 2 e to the t cubed sine 4t, because there's a 2x, but x is 2t, sine 3t squared. So you can see in front of you, x is becoming 2t, y is becoming t squared, z is becoming t cubed. So that's the substitution that we're making. All right, so then we have 3e to the t cubed cosine 4t cosine 3t squared, and then finally e to the t cubed cosine 4t sine 3t squared. All right, so that's a row vector dot product with column vector 2t, 3t squared of partial derivatives of g. Actually, they're just ordinary derivatives because it's a function of one variable. So now we can take the multiply corresponding components of this times this times this, and this times this, add them all up. That's what the dot product does. That's what the matrix multiplication is looking like in this case. So what we get is 2 times the derivative with respect to x plus 2t times the second component, 3e to the t cubed cosine 4t cosine 3t squared, plus 3t squared, the third component of this, times this, e to the t cubed cosine 4t sine 3t squared. And then you can simplify all that if you really want to. So as far as what derivatives are being matched with what we see is, so without filling in the actual functions themselves, we have df dx, dx dt, plus df dy, dy dt, plus df dz, dz dt. You can think of it as like there's a certain cancellation of the dx's. At least you can use that as a device to help you remember what partial derivatives to multiply with what. G is going to be a function that maps r2 to r2. So f of xy is x squared y plus xy squared, and g, function of s and t, it's a vector valued function like before. So we have two component functions, x and y, that are both functions of s and t, and those functions are 2s plus t and s minus 2t. So these are the functions we're going to compose. So f composed with g, function of s and t. So it's going to be 2s plus t squared, s minus 2t, plus 2s plus t, s minus 2t squared. So we're going to use a chain rule to figure out the partial derivatives of this function with respect to s and t. So like before, we have the gradient of f, so that's a row vector, fx and fy. So when we compute those, we'll have 2xy plus y squared and x squared plus 2xy.